And so let's go next step to locate a square wave. So we see there's a square wave in here that looks like an occultation. We are going to we're going to limit our search from around 150 to around 450, and that allows us to bracket the event and cut down on the number of possible searches done. And R-OTE puts in a maximum event duration of 270, which are the green bars, and that brackets our event, and a minimum event duration of 30, which is less than our event, so we know we're bracketing our event. In fact, we can increase these red bars even further to about 120, and that cuts down on the length of time it takes to do the analysis. Now we know our mag drop is around 1 from our path map, so we can reduce the amount of time it takes to run the analysis by limiting our mag drop analysis from about 2 times the mag drop to about half the mag drop. So we would go from 2 to about 0.5. That's a good bracket to make sure that we're covering the mag drop that we're expecting. So now we go to first pass, locate the event, and R-OTE's calculating surfaces. We have a little progress bar up here that runs, and now we're done. And we have a square wave fitted, and that's our first pass, which gives us a rough estimate of the noise, but it gives us the same noise in both the baseline and the event bottom. We want to analyze those separately now that we've actually identified where the event is. So then we can press update estimated noise values from the first pass, and that gives us the noise in the baseline separate from the event bottom, and you see that they are different, and that helps us improve our analysis. So now we're going to do a second pass, locate the event. Here comes our progress bar. Now we're done. Here's our event. Now we have data reported. But we're not ready to report out our results yet. We want to analyze the baseline noise now that we've isolated that by identifying the event. And in that we see that there's still a lot of variation that is correlated. So this is typically due to stars with heavy scintillation. Maybe the star has a low altitude. Could be due to some atmospheric effects. But when our Pearson R value is greater than 0.1, it means that we have a lot of correlation in our data, and that is an area where R-OTE is very valuable in applying correlated noise results to the error bars. So that's why we're running this analysis. So this file is saved to our folder. I'm going to minimize that. So once we analyze our noise, now we can calculate our error bars. And we see that the ACF coefficients have been transferred in. By ACF coefficients, I mean these are the correlations between any one data point and the data point next to it. And ideally, in random noise, the data point next to it would have noise that was uncorrelated to the first point. But we can see with these stepping down bars that there are as many as almost 10 adjacent points that are correlated to each other, That's due to either scintillation noise or maybe atmospheric effects like clouds. R-OTE will take care of that. So we've got those coefficients entered, and we press the button Calc Edge Histogram and do the error bar plot. So we hear a little bell. Let's see what that message is telling us. Press Alt-Tab. R-OTE says these coefficients are unusual. They cannot be used for generating correlated noise. And in fact, they're unusual because there are so many of them. But a lot of the tail end ones are very small numbers. And if we look and see, we typically only want to use the ones that are below about 5% of the total correlation. So we can cut it off at about 7 or 8 coefficients in this analysis. So if we go 1, 2, 3, 4, 5, 6, 7, 8, we get down to 0.713. Let's cut off this one here. We cut it off all these little tiny ones, and let's see if R-OTE likes that. And I see a little flashing taskbar here, and it tells me I've got a progress bar, so it is analyzing the error bars, which is what we want. We'll wait for this to finish. And we get 2 sets of histograms. One is for duration from R to D, and the other is just for D and or R. The duration is one that we capture for information and history, but it's not reported in our occultation error bar reports. So I'm going to minimize that down. And in this plot we see that we have 3 error bars reported. The 0.6827 confidence interval, the 0.9500 confidence interval, and the 0.9973 confidence interval by these vertical bars. The one that we will report is the 0.95 confidence interval. Now this particular graphic is also saved to the folder where we had the original CSV file. So I can delete it here for now since it's taking up space. So one of the things that's new in R-OTE 4.5.9, not only the way error bars are calculated, they actually calculate quicker now, is we've put some text that qualifies our error bar confidence intervals. And the key thing that we want to be sure and let our researchers know is that our error bars are actual distributions from Monte Carlo simulations, and they're not distributions that are parametric. Parametric are known distributions like Gaussian, student t, chi-square, log normal, something like that. Our distributions are unique. We've not found any distributions that match them that are parametric, and so the result is that the conventional parametric distribution, like a Gaussian distribution, the 1 sigma, 2 sigma, and 3 sigma are related by the 2 sigma is 2 times the 1 sigma, the 3 sigma is 3 times the 1 sigma. That's for Gaussian distribution. But in ours, we saw and I reduced it, but we can see it here over in our table that the 0.9973 is is around 15 times higher than the 0.6827. So that's clear evidence that these are not parametric distributions. For that reason, we're going to report out on our spreadsheet, our observer report form, in the future, all three of these, and the one that's used in particular will be the 0.95 that will be used in the occult for profile plots of the size and shape of the asteroid.